Welcome to Chapter 4, where we'll be looking at motion in 2 dimensions. This is Chapter 4, Problem 70. We'll be doing Part A and B first. The water in a river flows uniformly at a constant speed of 2.50 meters per second between parallel banks which are 80.0 meters apart. You are to deliver a package directly across the river, but you can only swim at 1.50 meters per second. So let's start with our given. We're given that our distance is equal to 80.0 meters. The river speed, I'm going to call that VW for V, water, is 2.50 meters per second. And we're going to say this way, okay, as our direction. And then our V swim is going to be 1.50 meters per second. Now in the first part, says if you choose to minimize the time you spend in water, in what direction should you head? So if we want to minimize the time we spend in water, let's say these are our parallel banks. So these are our parallel banks, which are 80.0 meters apart, right? So the water is always going to be pushing us. We just want to get across, and we don't care where we end up. So if we want to minimize the time, we should be going perpendicular to the current. In which case, the only velocity we're worrying about is the one going upwards. So for A, the direction we should head in is the one perpendicular to the current and banks. So essentially in that direction shown by the arrow. Now in part B, they're asking how far downstream will you be carried. So one thing we need to know first is how much time do we spend in the water. So we're going to split this up into our components because we have our swimming component and the actual current component. So let's just figure out how long it takes based on our V swim. So we know that distance is equal to velocity times time. So our time is the distance over our swimming velocity. So our distance of 80.0 meters over our V swim, which is 1.50 meters per second. So let's quickly do that. So we know that that is 160 over 3 seconds, which we can simplify to 53.3 seconds. Next, we will use this time to figure out how far downstream we move. So we know that I'm going to call this distance downstream because it's a different distance calculation. That's going to be equal to VW times the time. So that's going to be 2.50 times 53.3 seconds. And that will give us a value of, I'm going to calculate this out with hand, 106.6 plus 26.65. So we're looking at here 133.3. And that is going to be essentially how long it takes, or how far, 133.3 meters is how far downstream we're moving. So that's our part A and B. So we've got perpendicular to the banks and 133.3 meters. So we're continuing problem 70 from chapter 4 in this part C. It says, what if? So in this problem, they want to say, if you choose to minimize the distance downstream that the river carries you, in what direction should you head? So here's a quick diagram. So we have our current, which is moving this way, and that's 2.50 meters per second. We'll take a look at that later. Right now we're worried about our swimming, and we know that if we move straight, we're going to be pushed this way by the current. So the idea is that our velocity vector for swimming is going to be somewhere in this quadrant, because that way we get some force, some velocity to oppose the current, and we're still moving forward. And we need to find that sweet spot angle. So there's two ways to solve it, and I'll go through both. One requires a bit of calculus, or you can just use your calculator. The other one's a bit more intuition, but not as valid of a solution. So here, we'll start with this one. We'll start with the mathematical valid one. So here we have Vx. So our x direction velocity is the speed of the water, right, the current, minus Vs sine theta. So we're going to call this theta, okay? The actual angle we want is right here, but we can just shift that later, 90 minus, so that's not a big deal. And then Vy is Vs cosine theta, so it's this one right here, this vector right here. So now we know the distance between this bank, so I'm going to denote that by d. So the distance divided by our Vy, which is Vs cosine theta, is the actual time we're going to be in the water. So therefore, delta x is going to be, delta x is how far downstream we end up. And that's going to be our Vx times the time. So we're going to have Vw minus Vs sine theta d over Vy. And then it simplifies to this. So we get that. We get Vw d over Vs cosine theta minus d Vs sine theta over Vs cosine theta. The Vs's cancel out. So now we continue here. So this is what we get next. We get Vwd over Vs cosine theta minus d tangent theta. We can factor out the d. So we're left with this little thing in the parentheses, Vw over Vs cosine theta minus tan theta. We want to minimize this. So how do we minimize this? Well, let's plug in some values that we already know. We know that Vw is 2.50 meters per second, and Vs is 1.50 meters per second. So we can make that phi third. I'm going to make the secant theta, which is just 1 over cosine theta, minus tangent theta, d. So there's two ways we could do this. The first way is we could graph it on a calculator, which is probably what they would like us to do at this point. So I'm going to graph it. We can do 5 divided by 3 cosine theta. And that is going to be minus the tangent of that. I'm going to just shift the mode real quick to radian. I'm going to graph that. Alright, so we want it where it is minimized, pretty much. So we're going to set the window right here. Let me fix this window. So we get this unusual, funky looking graph. Oh, one second, let me adjust this real quick. So we want it pretty much where it hits that infinite point where there's no value to it. So you can calculate that with your graph, actually just put in the points, but I'm going to show you the calculus way, which works a bit better. We're going to have to go through this. So we can use derivatives to find minima, which, I mean, that's a calculus idea, but I'll just go over this. So we know, I'm just going to give you some formulas. So derivative of secant, which is pretty much the slope of this graph, is defined as this. So that's just general formula. And the slope of tangent of theta is that. So now I plug that in here, right? And I get phi thirds secant theta tan theta minus secant squared theta. Now I can factor, right? And I want this to equal 0, because the moment the slope equals 0, we get our minima, right? When this is equal to 0, we get the minima. So secant theta equals this. Now secant theta can't equal 0, because that would mean 1 over cosine theta equals 0. So that's not the correct value. So we're going to look at this part. So I'm going to make that equal to 0. So I get phi third tangent theta equals secant theta. So phi third sine theta over cosine theta equals 1 over cosine theta. It's getting kind of complicated. But essentially we get sine theta equals 3/5. I put this in our calculator and we get sine inverse of 3/5 equals 37 degrees. And that was from the normal, remember? They want it from the bank, so our answer is 53 degrees. And earlier I said there was an intuitive answer. Now their answer, this is not very valid, but I figure if you don't want to use your calculator or calculus as earlier, we can use this. So the idea is you want to minimize your resultant. You want to minimize your resultant right here. You want to minimize the angle with the normal. So pretty much what they said is that theta, if you know this is 2.50 and this is 1.50, the way to minimize it would be to take the cosine of theta to equal 1.50 over 2.50, and that would be 3/5. So if you take the cosine inverse of that, sorry, we're in the wrong mode, 1 second, let me change degrees. We get 53, so it's the same idea. So that's our answer, 53 degrees, however you want to come to it. And then now here's our next part, the distance downstream. This is a bit more complicated. So, or actually this part's the easy part, sorry. So we know that sine theta equals 3/5 from earlier, right? We showed that over here. And based on that, cosine theta equals 4/5. You can just prove that using the formula that cosine squared theta plus sine squared theta equals 1. Not too hard to prove, but you get there. And then tangent of theta is 3/4. Now the reason I wrote these down is we're going to need them when we solve delta x. So earlier we said that delta x is equal to, I have all these numbers written out, but what it really was equal to was, let's go back over here. So it was equal to VW minus VS sine theta, that's our VX component, times the time, which is D over VY. Okay, so now, and then we simplified it later to be D times VW over VS cosine theta minus tangent theta. So now we get that, right? So our distance is 80.0 meters, and then our VW over VS is 2.50 meters over 1.50 meters per second, times 5/4, which is essentially the opposite of cosine theta. Secant theta is 5/4, then minus 3/4. So this is just a lot of numbers, but it simplifies down to 80 times 25 over 12 minus 9 over 12, which is this, and then which is 80 times 80.0 times 4/3, which is 320 over 3, or 107 meters. And that is our final answer. So we have found the angle from the bank, and we also have found delta x given, as earlier stated, VS, VW, and the distance between the banks. So that is all we need, and that is how we came to our answer.